Okay, so today we're going to finish up graphing trig equations. I know this is probably going to be a little more difficult of a day. So, if you're having any trouble in the class, please feel free to reach out to me. I have office hours. If those office hours don't work for you because you work, let me know. We can do other office hours, for extra tutoring. Of course, there's always the Math Learning Center. But I would highly recommend you spend a lot of time practicing in this part of the class. It is a little like we're now going to start getting into material that's a little more difficult, not just time consuming. All right, so graphing a cosecant. So cosecant, if we remember, is equal to 1 over sine of x. So whenever we have a function that has a denominator, we have to worry about the denominator, right? So Alex, what do we have to worry about for when we look at the denominator?
Uh, I think it can't be.
I know you know this. It's okay if you
I
can't.
know it can't be zero, right?
It can't be
Or
zero.
yeah.
Exactly.
All right.
Exactly. Exactly. So we look everywhere that if we had x in there, that the sign of it, that would be zero. And that's at 0 and pi, right? For sine, it's at 0 and pi that it equals 0. If we remember the unit circle, and sine is the y value. On the x-axis, the y is going to be 0, and this is 0 and pi and 2 pi and 3 pi. So all multiples of pi, right?
Mhm.
Okay, so that's what this basically says. So we have our domain is all real numbers from negative infinity to positive infinity, except x is not equal to some multiple of pi for the exact reason we just said. This black line that's in there, that's the graph of the sine.
Mhm.
So that doesn't need to be graphed. That's just it's more the author of these slides. I thought it might be helpful to show you, like, the sine graph is what this is really based on. It's 1 over sine. So like everywhere that the sine is 0, which is here, 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 we can see that we have asymptotes there, right? So cosecant, all the graphs we're going to go over today are going to have asymptotes because they all have a numerator and denominator. We're going to go over cosecant. I'm just going to tell you the difference between cosecant and secant. I don't want to go over it in detail. Tangent, and then we're going to do cotangent. So all of those are functions that have denominators. So they will all have asymptotes. And again, the first thing you want to do is graph the asymptote. And then why does it look like it does? Well, if you think about what's happening, everything on the unit circle, the sign of anything, what's the range for the sign of x?
Negative 1, 1.
Yes. So the range is going to be of the sine function is from -1 to 1. So let's think about any number between -1 and 1 except for 0. Well, let's look at let's look at the outsides. Oh, it includes -1, sorry, and 1. Okay. So let's just look at the -1 and 1. So let's look at when the sign is equal to 1, then this function equals 1, right? 1 over 1 would equal 1. And so where does sine equal 1? It equals 1 at pi over 2 and 3 pi over 2 and so on, right?
Mhm.
So you can see that that's where, let me get a different color. That's where these points are coming from. Those are 1 over 1 is 1, and it's at pi over 2 and negative pi over 2, right? And 3 pi over 2. And that's why it's 1. And then what we want to do is look at in the middle. So let's look at something less than 1 and greater than 0. So let's look at 1/2. And if I have 1 over 1/2, what does that make the value equal to? What would cosecant be if I had 1 over 1/2?
Over 1/2.
Yeah,
Wouldn't that be 2?
it would. So 1 over 1/2, it just flips it, makes it 2. So notice as the values of the sign get smaller, or are between these two values, they're like if they're between 0 and 1, they're just going to get smaller and smaller, right? And the smaller the denominator gets, the bigger the function gets, right? Because this is equal to 2. If it was 1 over 1/10, it would be 10. And so what's happening is that's why it's going up from there instead of down, because the reciprocal of all those small fractions become bigger and bigger. Okay, and the same thing we can say in the negative direction. If it was negative 1/2, then it would be -2, and that's why it's going down on these in the negative side. Does that make sense?
Yeah, I think it, yeah.
Right, because it can't get it. There's no way it can go, like there's no way that 1 over, let's just call it z, which is the sign, could be between 0 and 1, as long as I can't make z greater than 1, right? If I can make z greater than 1, then it becomes a fraction that's smaller than 1.
Yeah.
But otherwise I can't. And all my fractions there are tiny. Or else you can look at this as, you can multiply everything by z, and then this would be 0 is less than 1 is less than z. So yeah, so I like z would have to be bigger than 1, and it can't be. The denominator can't be bigger than 1. So that's why it can't be that small. Does that make sense now? Is that helpful?
Yeah, that makes a lot more sense.
Okay, good. So that's basically what the cosecant function looks like. The only difference between cosecant and sine is going to be the secant. I'm sorry, the only difference between the cosecant and the secant is that the secant is 1 over cosine. So we'll have different asymptotes, right? Our asymptotes, instead of being at pi, will be at pi over 2, everywhere that cosine is 0. So cosine is 0 at pi over 2, 3 pi over 2, and so on. So basically, all that does is shift the graph. The graph still looks the same, okay? And I have a picture of the secant, and you can see that it's exactly the same, except we can't have odd multiples of pi over 2, because that's where the cosine is equal to 0 at pi over 2 and 3 pi over 2 and different values of that. So do those secant and cosecant graphs make sense to you? I mean,
Yeah.
I know making sense and doing them yourself are two different things, but I'm just wondering if like you understand at least how they're working.
Yeah.
Okay. I'm not going to focus a lot on secant and cosecant because I don't think they should be a big focus. We don't really graph secant and cosecant that much. I think you should know what they look like, and that, but I wouldn't focus on them. I guess I probably should say, I probably won't put them on a test because I just don't think that they're important enough. But tangent is. So again, when we talk about tangent, we want to talk about that it's really the same as the sine of x over the cosine of x, right?
Mhm.
So again, when we want to graph it, we have to think about, well, I can't have my denominator equal 0. So cosine of x cannot equal 0. So where does cosine of x equal 0?
At 0?
No, think about your unit circle. These are all just translated from here.
Mm.
So what's the point here at 0? So x equals 1, y equals
0,
0,
1,
right?
0. Okay.
Yeah, so cosine is 1 there. because cosine is the x value.
Mhm.
How about up at pi over 2?
It's 0, 1, so it's
0,
0.
1. So it's 0. Again, cosine can't be 0, which means that at pi over 2, we have to have another asymptote,
Okay.
right? Make
Yeah, that
sense?
makes sense.
And the same thing here. Let's look at negative pi over 2. At negative pi over 2, we're going to have another asymptote if we're just looking at one cycle here of the tangent.
Mhm.
And here we can also see that tangent has a period, and I think we've talked about this already. I'm not really actually sure. Have we talked about the fact that the tangent has a period of 1? I don't think we actually have. So
No.
no, we haven't. So here you can see that from negative pi over 2 to pi over 2 is actually only 1. I'm sorry, only 1 pi. So we have the period for tangent is just going to be pi, which is different than all the other functions, right? Because sine, cosine, secant, cosecant, they're really all based off of 2 pi. So tangent and cotangent have a period of pi. It repeats every pi. And then so we always put the asymptotes in first. So we know that our asymptotes are at pi over 2 and negative pi over 2. And then the next best thing to do is find where our zeros of the graph are. And when I want to find where the zeros are, what am I looking at in the function? Do you remember?
Uh,
Same thing was with rational functions. When you want to find the zeros of the rational functions, where in the fraction is it? Do you need to worry about?
is it the denominator?
The numerator, right? Because when
Numerator.
the numerator is 0, everything's 0,
Yeah, yeah, yep.
right?
Okay, that
0
makes
or
sense.
anything is still 0.
Mhm.
So we want to figure out where this, so for the zeros, I'll write it over here. For the zeros, we want to figure out where the sine of x equals 0. And we'll look at our graph. We'll look at our unit circle and we can see here that the sine of 0 is 0. And there's our point 0, 0. Okay.
Mhm.
So so now we've graphed our asymptotes. We've graphed our 0. And then what we need to do is be able to graph, and Alex especially, you need to be able to graph another point on either side of the 0, basically between the asymptotes, okay? And we want to find a really nice, easy point to graph. You can graph any point. As you can see, there's and there's more points than that. So there's an infinitely many points you could graph, but there's one real easy one to graph. Do you have any idea what that one is?
Would it be like, oh, the pi over 4?
Pi over 4. Good
Yeah,
job. Good job. Because at pi over 4,
it's
we
1.
have square root of 2 over 2, comma, square root of 2 over 2. So sine and cosine are equal to each other. And when we put the one over the other, we get our point, pi over 4, 1.
Hmm.
And so that's that point. And then doing exactly the same thing in the negative direction. This would be square root of 2 over 2, comma, negative square root of 2 over 2. So at negative pi over 4, which is right somewhere here, right here, we have negative 1. And then we just connect the points. And basically that gives me my shape. And this, I'm going to show you another graph of it going out here forever. So here's what it basically looks like when we go from negative infinity to positive infinity. And we have, again, our asymptotes at all multiples, odd multiples of pi over 2. Okay, the last slide showed us just this right here, the one closest to the origin. Okay.
Mhm.
Any questions about that?
I don't. I'm sure I'll have one later.
Okay, no problem, no problem, no problem. Okay, so let's look at the properties of the tangent. So the domain is the set of all real numbers. So it can go from negative infinity to positive infinity, except odd multiples of pi over 2. Those are where our asymptotes are, right? The range is all real numbers. When we look at it, notice we can go from negative infinity to positive infinity for our range. There's no trouble there. Okay. The tangent is an odd function, and its symmetry has with respect to the origin. Do you remember how to tell if something has symmetry with respect to the origin?
If it's, I thought it had to be an even function.
Well, let's try to remember what the difference between odd and even functions are. So odd functions and even functions. So odd functions, the main rule for an odd function is that f of minus x equals minus f of x. This is the definition. And for even, it would be f of minus x equals f of x. Okay. So let's think about what this really means. If I have a function and it's odd, let's say I have a negative x value, right? Let's say whatever this value is, this is negative x, and we'll make it here, this point, whatever that point is, okay? Now, if that point is f of negative x, then what's going to happen to this point if I say that it's the same as f of x? Let's call this, let's just make it 1, who cares, right? So negative 1. So we have a point at negative x equals negative 1. So if I have that, that means at positive x, this has to equal positive 1, right? That's only if this equals negative 1 here, then this would have to be positive 1, so that when I added on this negative sign, they're equal, right? So that means I have another point here at positive 1. And so notice how it's mirroring around the origin. Okay. So I could connect these two dots. This is an odd function because, and I could even say this is actually just y equals x. Y equals x is an odd function because let's see. So if we have f of x equals x, and let's say x equals 1, then actually, let's not do it that way. Let's say, well, then f of negative x is going to equal negative x, right?
Yeah.
And so to make these two equal, can't I say f of negative x equals negative f of x?
Yeah.
And that makes it odd. So that's so basically what you want to be able to do if something's odd is if you can flip it upside down and it doesn't change the way it looks, that means it's odd. Like no matter if you flip it completely upside down, 180 degrees, then it will look exactly the same. And if you have a laptop or you want to draw this on a piece of paper and then flip it upside down, you'll be able to tell that it will look exactly the same. Okay, so that's what reflection around the origin is. If you flip it upside down, basically it'll look the same. That's a visual explanation. Okay.
Okay.
So for even functions, this is a little different. Let's look at something that's even, maybe a parabola. So we can say that here's negative x and here's positive x. And notice the y values are the same, aren't they?
Yeah.
That's what this means, that if I go in either direction, it's still going to be the same. The y values are the same. So this would be have symmetry.
I think, okay, I remember this now.
Around yeah.
That clicked.
Okay, good. So yeah, so even is always around the y-axis, odd is around the origin, and the origin basically is just flip it upside down. I mean, odd and even will come in, we will talk about them more and more as we go. So I don't want to leave that out. So the tangent function is periodic. And as I said before, this is the tangent and the cotangent are the only two trig functions that have a period of pi. Okay. I wouldn't worry about these two things. These two things you can figure out on your own. I wouldn't memorize that. It's just we're trying to find out for the x-intercepts. This shouldn't say, yeah, this is just where y equals 0. Okay. And the vertical asymptotes is where the denominator equals 0. I mean, that's what you should just remember for what x-intercepts and vertical asymptotes. I definitely wouldn't try to memorize that. So for example, let's draw a graph of tangent. So let's start off. So how are we going to start? What's the first thing we're going to do? Do you have any ideas how to start graphing y equals? I just want to graph tangent of x. That's all I want to graph.
There's no. Okay, well, I know that it's down 1.
Yeah, we're not doing the down one, we're doing the tangent. If you can't graph the tangent, you can't really move it.
Well, it starts at 0, right?
Well, let's get a plan instead of just kind of trying to pick stuff up. Okay.
Mhm.
So maybe this will help. I'll try anything. So let's have a plan. Step 1, we want to find our asymptotes, don't we?
Mhm.
We always, whenever something has asymptotes, we want to graph those first. Remember my cow story?
Mhm.
From rational functions.
Yeah.
I know it's a stupid story, but usually people remember it. So if I want to find the asymptotes, I know that we have tangent of x, which is equal to sine over cosine, right?
Mhm.
How do I find my asymptotes? I only have vertical asymptotes.
Yeah, I know that, but
You know how to do it. I know you do.
I do.
You
Okay,
already
so
told me
that
today.
means that it's the same way as. I don't know. I'm drawing a blank though.
The denominator equals 0. You've got to remember that. I mean, these are things you can't forget because they will not go away. Okay. Like when you want to find a vertical asymptote, how do you find it? The denominator equals 0.
Yeah.
Write it down, tattoo it on your arm, whatever you need to do to not forget. Denominator equals 0. Don't write it on your arm for tests.
Yes.
So where does cosine equal 0? Again, we look at our unit circle. Where does cosine equal 0?
Oh, so pi over 2, right?
Right, pi over 2. We
And
have an
negative pi over 2.
asymptote. Yes. And negative pi over 2. And 3 pi over 2, right?
Yeah, okay.
And negative 3 pi over 2, and on and on and on. Okay, so first step, asymptotes. Step 2, zeros. We want to set numerator equal to 0, right?
Mhm.
Or and x equals, no, when I find the x-intercepts, we want y equals 0. So we want y equals 0, which is the same thing as the numerator has to equal 0. So where does the sine of x equal 0?
Pi, negative pi.
Pi, sure, pi, negative pi. Don't forget 0.
Yeah.
That's the one that's a very important one. Okay. And then I have to graph 2 more points, one on either side of that x-intercept. So I have to graph 1 point between 0 and pi over 2. Let's write it like that, okay?
Mhm.
And you already told me which point's a good point to graph, right?
Yeah.
You remember what you said?
Pi, what do you mean? Like,
Pi over 4, yeah.
okay, pi over 4.
Yeah,
Yeah.
pi over 4, yeah. So there's 1, and so there's our pi over 4. Okay, here's our 0. And then also we want to graph something between negative pi over 2 and 0. And again, that would be negative pi over 4, right? Would be negative 1.
Mhm.
So we have that point on our graph, and then we just connect them. And the same thing is true here. We're going to have the same exact situation happening here, and it's going to just keep repeating everywhere. Okay, I know this isn't a beautiful graph, but let's just call it tangent. Okay, so now, good. Now we have our tangent graph, and then we want to do our transformations. So what's our transformation that we need to do first?
The down 1.
So
Do the other one for
if I gave you a value for tangent, let me say I told you tangent equals 1, would you subtract 1 first?
no,
What would you do?
I so we stretch it first.
Yeah, so we multiply by 2 first, right?
Yeah.
So be careful if you do things out of order, it won't work. Because if I move this down 1, think about what's going to happen. If I move this down 1, then this point right here is going to go to 0. And when I multiply it by 2, it's still going to stay 0, isn't it?
Mhm.
So you have to be really careful about the order you do things in. So first thing we have to do is multiply by 2. Okay, so to multiply by 2, all I really have to do is change these values here to 2 and minus 2. Same. I wouldn't do it any differently. And then down 1 basically just moves these points down 1. So it'll look pretty much the same everywhere, except it'll look kind of like that. It'll still go to the asymptotes. And so that's kind of what we're doing. I'm going to show you in more detail with a chart when we start doing a lot of transformations, because I think that that's going to help. But I think for this, what you really want to do is find your original points. So our original points were at, let me see how I want to write this. Okay, well, we can do a table. So we have our x and our tangent of x. So when x is 0, tangent is 0. When x is pi over 2, I have an asymptote. Negative pi over 2, I have an asymptote. And then pi over 4, I have 1. Negative pi over 4, I have negative 1. Okay, so let's start there. And then what we can do next is we can say, okay, well, I'm going to multiply all these tangent values by 2, right? So 2 tangent of x would be 0, asymptote, asymptote 2, negative 2, right?
Mhm.
Let me kind of do this here. I'm going to we don't need this one out here, and I could use the space. Okay. And then, so now I found my 2 tangent of x, and then I could say 2 tan x minus 1 would give me, well, this would be negative 1, asymptote, asymptote, 1, negative 3, right? And now I have my x value. My x hasn't changed, but my y value's changed. And so I can easily plot these points, 0, -1, and so on, right? Those 2 points go together. So I think this table, like starting to write these things in a table form might really help you get the points you're looking for.
Yeah, that seems like that would help me organize it better.
Okay, good. Well, I was going to do it. I was going to do it a lot in a little bit, but maybe now is a good time to start figuring out how to do the transformations just kind of easily through a chart.
Okay.
So did that all make sense now?
Yeah, that made more sense.
Okay, good. And then we have cotangent. Cotangent, notice, so our tangent graph, let me show you a picture again. It's going, it looks like, I mean, it looks closest graph that we have to that is like an x cubed graph, right? But cotangent looks exactly the same, except it's flipped over the x-axis, right?
Yeah.
There's something else different about it though, because cotangent equals what?
Oh,
What did we say tangent equals? As far as sines and cosines?
is it? I know it's flipped.
It is. So these are, so the things without like, I'm not trying to say anything bad. I'm just trying to like,
It's cosine over sine.
what? Yeah.
Cosine
So I
over
just
sine.
want to explain, like, there's certain things that you're going to have to really start, like when we learn something, you're going to have to learn it for a long period of time. You know, like like maybe if you learn history, you're going to learn history and you just need to pass that test. And so you can like learn it for like in short-term memory. The things that we're learning now have to go into long-term memory. Like these are not just things that I'm saying that you won't need again. These are things that I'm saying that you're going to need through the entire semester and onward through your engineering career. Okay, or at least through your engineering math career, for sure. Okay, so you have to start putting some of these things into long-term memory. Okay, okay, so cotangent is, and I'm not just talking to you, I'm talking to anybody who's watching the, you know, I'm not talking specifically to you, Alex. But I can see some of the problem that maybe what some people are having by how you're speaking. So again, cotangent is really the same as tangent, except our sine x is now our denominator. So our, notice here, well here we can, I guess we can go back and look. Here it's odd multiples of pi over 2 is where we can't have x, or that's where our asymptotes are. Here our asymptotes are at multiples of pi. So what we've done is shifted the graph and then flipped it. So it's more than just a flip over the x-axis, and you can't say cotangent is the same as negative tangent. It's not. It's shifted. So it's really important if I'm asking for the function that this graph represents, the first thing you need to do is figure out where the asymptotes are. So since the asymptotes here are at all the intervals of pi, or all the multiples of pi, I know, well, since asymptotes are in the denominator, and I need to know where my zeros are for sine, my zeros are at 0 and pi. That gives me the cotangent. Does that make sense? Like,
yeah.
if you have, like, the asymptotes are changing, that's how you can identify the graph. Of course, you can say it's equal to a negative tangent that's shifted, but that's way harder than just saying it's a cotangent. Okay. And again, cotangent is not as important as tangent, but how things work is. So that's where like I do want you to understand what's really happening. And you will have some Alex homework that'll make you have to understand these things. Okay, so transformations of the graph of y equals sine. So basically this is just sinusoidal graphs, which is just sine and cosine are sinusoidal because they look like that. Okay, that's what a sinusoidal graph would look like. And we're gonna just go over and remind you of some of the characteristics. So the absolute value of A, or this value in the front, gives us the amplitude of the graph. We can call it the maximum displacement from the average value, but I would just call it the amplitude. Yeah, it's really our multiplier. And again, B is related to the period of the graph. We said that the period is equal to 2 pi over B. But now we've added, this is true for sinusoidal graphs. But remember, I gave you kind of a new way to say this, is that the new period is equal to the original period over B. Because for tangent and cotangent, my original period is not 2 pi, it's pi. So we have to be really careful about that. It's not always P equals 2 pi over B. It's P equals the original period, which for sinusoidal graphs is 2 pi over B, okay? So we're dividing all our values by this B that's in our form, okay? All right, so now why do we have this standard form and this shifted form? Well, we use the shifted form to see what's really happening as far as our horizontal shift. We have to what we're doing. The difference between these two is this one is B is factored out. Of the argument. You see that?
Yeah, I did.
So basically all we do, if we divide both of these pieces by B and we put that out front, then that's how we get our shifted form. And we're gonna mostly be using our shifted form. How come? Hold on a second. Okay, my mouse isn't dead. My mouse was dead. Okay, so we're basically gonna be using our shifted form for a lot of what we're gonna do. So in either case, C is called the phase angle, which we're not going to really talk about much, but we are going to talk about C over B, which is the horizontal shift. Okay, so C by itself is not the horizontal shift. And then we know that D gives us our vertical shift. Okay, because it's outside. These two are our vertical outside. These are vertical. And anything inside is horizontal. Okay? Is there anything here that I need to explain further, or you're good with all that?
I think I'm good with that.
Okay. So, okay, here we go. So well, this one isn't, yes, and we're not going to do this part. Don't worry about this. Don't worry about the primary interval. So here what we're going to do is we want to identify the amplitude, period, horizontal shift, and vertical shift. Okay, so what's my amplitude?
Amplitude would be, isn't it half of the A?
No, it's A.
No, it is A? Oh, okay.
It's just A, it's just 2.5.
Okay.
Our amplitude is 2.5. Because that's my multiplier. I'm gonna, like, all the positive values can be multiplied by 2.5 and all the negative values can be multiplied by 2.5. So from top to bottom, it's double that, if that's what you're thinking. You're right, it is double that from top to bottom, but the amplitude is 2.5. Okay, our period, well, any ideas?
Is pi over 4?
That is not our period. What would we call that? So remember in the last slide, we saw that f of x equals a sine of b x plus or minus c and then plus d, right?
Mhm.
Okay, so what of these things affects the period?
Doesn't 2.5 affect the period?
Nope. 2.5 affects the amplitude. So if
Yeah,
I
but
have
damn.
something like this, so this is the amplitude. So let's say this is 2.5, right? And this
Yeah.
would be negative 2.5. That doesn't change the period. What I'm talking about with changing the period is I could either stretch this graph wider or I can make it go faster, right? So
Mhm.
that's what affects the period. That's what something in here changes the period. So remember, I just gave it to you. The
I
new
know.
period is equal to the old period divided by B. Or well, I don't want to say old, I should say original. Remember, I just told you that.
Yeah, can
And
you
what's our period for sine?
can we go back to the last slide?
Yeah. You want to take a picture of it?
Yeah. Okay.
So what's our period? What's our period for sine, cosine, secant, cosecant, all the same period?
Is it that middle part? So like
And no, it's just 2 pi. So original period is 2 pi. Right? So what we're talking about is my original period for sine, cosine, secant, cosecant. They're all 2 pi. I'm trying to find the new period. And then I need to divide that by b. Do you know where b is?
he is 4?
Pi over 4,
Pi over 4, okay.
right here. This is b, pi over 4, right?
Mm-hmm.
And then if I divide 2 pi by pi over 4, I get
5 over 4. Is it 8?
8, exactly. So my new period's 8. So we found our amplitude, we found our period. Now I want to find my horizontal shift. Well, let's do our vertical shift. Our vertical shift is easier. So let's do our vertical shift. What's our vertical shift equal?
6, up 6.
Yeah, up 6, positive 6. Okay, now what we want to do is find a horizontal shift. And it's not so easy in this form because it's not 3 pi over 4. Okay, so that's why we have that shifted form that maybe you have a picture of.
Yeah, I see it.
Okay, so what we're going to do is we're going to factor out, we have to factor out that
Pi over 4.
4. Yeah, so we're going to put this in shifted form and we're going to say this is equal to 2.5 times the sine of pi over 4 parentheses t plus, and then what would I get for my next value?
3.
Exactly. Good. So now I know my horizontal shift.
Oh, okay, so it's left 3.
It's left 3, or we would say negative 3. That's what Alex wants you to say.
Oh, okay.
3. Okay.
Okay.
Okay, good. So that's why we do need to know do need to be able to transform this. This is the shifted form.
So the period is just basically like I don't it's like the length.
Yeah, it's how fast it's going through so if this is a graph of a period, then if I want to make it if I want to make it go faster, you know what I'm saying? If I want to make it go faster, then what I have to do is I have to compress it. When I compress it, I'm actually making this, I have to make this B, the bigger the B gets, the longer. So this is B is greater than 2 pi. It just gets bigger. It gets wider. Okay. This is B is between 0 and 2 pi. We're going to compress it. Notice pi over 4, we're compressing it a lot. So normally we would have a period of 2 pi, but now we're compressing it by pi over 4, actually not by a lot, but instead of it being like 6 point something, our period is now 8. So our pi over 4, which is 3 over 4 approximately, right? So it is going to get a little longer. It's going to stretch because it is bigger. So I got that backwards. It's not, it's, hold on. So when B is greater, yeah, the bigger, no, when B is greater than 1, that's what I want to say. Sorry about that. Yeah, that's what's wrong with this. So we're really talking about when B is between 0 and 1 and when B is greater than 1. Yeah, that changes the period. So here, it's going to get longer. Let's see. So the smaller that the B is, the longer it gets. So this is when B is between 0 and 1. And this is when B is greater than 1. And this is when B equals 1. Okay, does that make sense now? So the larger, wait, I think I have that wrong too. Hold on, give me 1 second to make sure I get it right.
Mm-hmm.
The bigger B gets, yeah, the bigger B gets, the tighter the curve gets. I have it right. The smaller B gets, the longer. It's the opposite of vertical.
Okay.
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 So this is 3/4. 3/4 is between 0 and 1. So this one would stretch out. And we'll see it in a minute. I'll do it. I'll do an example problem. Any questions?
No.
Okay, so we're looking at this graph, and what I want to do is I want to find an equation for it. So I'm going to start with, and again, I'm going to start, especially when I'm starting with a graph, I can see shifts. So I have to start with my shifted form, right? So I'm going to say this is A, and then we need to just pick, should we use sine or cosine? Oh, never mind, it tells us sine. So A sine of B times X, and then I'll just say, I guess, plus C over B, and it may be negative, I don't know, and then plus D. Okay, so we have to fill in all our pieces. Okay, so what piece do you want to start with first? Usually, I would say probably the easier ones are the A and the D, right?
Mm-hmm.
Okay, so let's start there. So how do I find my amplitude?
Wouldn't it be like, is it 200 or no? No, what is?
Not 200. No, I'm not sure how you're getting it.
Is it?
So the first thing we want to think about is where's the middle, right? Like, because when we graph a sine function without transformations, it's going to look like this, where this is my amplitude, right?
Mm-hmm.
So if it's shifted, which it's obviously shifted, or because it's not moving up and down around the x-axis, so it's obviously shifted. what we want to do is still find our middle because, or there's two ways we could do it. So we find our middle, we can find A because it's just the distance from the middle to the top. Or if we want to, we can say it's half of the total range, I guess we could say, half of the range, right?
Mhm.
So maybe range is not a good word. Half of the y, or half of the height. That's probably the best way to say it. Okay. Half of the height.
So is it 125?
I believe it's actually, yeah, it is, because we can see that here's really the middle of my graph, right where these points are. And we can see that it goes, and this is at 175, right?
Mhm.
Can you see that that's the middle and that's at 175?
Yeah. Mhm.
So I can say either it's the amplitude, I can do it this way and say it's 300 minus 175, which is 125, or I have some kind of virus on my thing, or I can say it's half of the height, and the height is from, or I can say A equals 1/2 of the height, which is 300 minus 50, which is still going to be 125. Either way, it works. It works. Okay. So now let's start filling our graph, our function equation in. We have A equals 125 sine of, and then we haven't done, we're not going to do the inside. So will that help me with finding what my D equals?
Y-
What does D represent?
or a shift that's
Right, vertically or horizontally?
vertically.
Vertically. So we want to know how high it's gone, right? How much it's shifted from where it normally is to where it is now. And that's actually kind of easy because remember we said the middle of the graph is this line at 175, right?
Yeah.
So that means that that should be on the x-axis if we didn't shift it. Isn't that true?
Yeah.
So our vertical shift is 175. Does that make sense?
I mean, I see how you got the number. I just don't understand.
Well, normally sine graphs go up and they go as much above as below the x-axis, right?
Uh-huh.
So if I'm going to shift it up and I want to still know what the amplitude is, well, I need to find the middle of the graph, because the middle of the graph here, isn't that y equals 0?
Yeah.
So if I'm shifting it up to, let's call this a sub 1, right? My new 0 is at y equals a sub 1.
Yeah.
So how much have I shifted it? That amount, wherever the center is of the new graph,
Okay.
because it should be going like up and down, around this x-axis, right? Like
Mhm.
we have something looking more like this around the x-axis. Sorry, I didn't win 10. Oh, sorry. Like if it was just an unvertical shifted graph, then it should look something like this, right? Where it's going up and down around the x-axis. But how much have we shifted it up? We've shifted it up that much.
Yeah.
No. Yes? No.
Mhm.
Make sense?
Mhm.
Okay, good. So that's our shift. now the hard part, right? So now we want to find our B and our C over B. So the first thing we really need to find is our B, is our period. So we have to find our period. And our period, I'm sorry, we have to find our B, but our B is what's affecting the period. And remember, we have our equation that says our new period is equal to our original period over B. Right?
Mm-hmm.
So what's our original period for sine?
Isn't it? It's 2 pi.
It's 2 pi. Very good. Now we have to figure out, we don't know what B is, and we can't find B, but we can find the period of this graph. Okay? So how do you find the period of a graph?
You take the, don't you take like the highest number, the lowest number?
Well, the period is a period affecting the vertical or the horizontal?
Horizontal.
Horizontal. So what's my biggest horizontal value minus my smallest horizontal value? That doesn't make much sense, right?
No, that doesn't make much sense.
Okay, good. So how do I find the period? What is it? What's another word for the period? Do you know?
No.
Like a cycle, one
Okay.
cycle. See, that's why here we look at the period, we can say, well, this is one cycle, right?
Yeah.
This is one cycle, and then it repeats. So we can see for this cotangent that our period here is pi, because between 0 and pi, it has one period, okay?
Mm-hmm.
So if I want to find the period, I have to find one cycle. And to find one cycle is not that difficult. I just have to pick a starting point and an ending point that are the same. So like, for example, I can say these 2 points right here represent one cycle, because it's going up, it's coming back down, and it's going back to the same point, and then starting over, it's going up, it's going to go down, and then it's going to come back to the same point, right?
Yeah.
So
What is it? Uh, eight.
it's not 8. So this point here, what's this value is 2, and
Mhm.
this value is 18, right?
Yeah.
So what would be the new period?
Oh, I went too short. Okay. So
Yes,
it's 16.
16, right? You can pick those 2 points, or you could pick these 2 points. Those are still one period,
Yeah.
okay? And that's 22 minus 6, which is still 16. So, or you could pick this point and this point. That's still the same period. But we're just finding any 2 points that go through one full cycle and subtracting them, okay? And we're going to always get the same value, 16. So now we have 16 is equal to 2 pi over b. So what does that mean b equals?
2 hours. Mm, wouldn't it equal 16?
Nope, we're solving for b.
So it's
If b was 16, would 2 pi over 16 equal 16?
no.
No. Just solve for it. You don't have to like know it, just solve for it. So let's multiply both sides by b and then divide both sides by 16. Wouldn't I get b equals 2 pi over 16,
Yeah.
which is pi over 8?
Oh.
That's all I'm doing. I'm really not doing anything that fancy here.
Okay.
I'm really not. I wish I was doing something really cool, but I'm not. Okay, so now we know b is pi over 8. And we can say times x, and then we have to figure out what our shift is. So we look at our graph, and where does my sine graph normally start?
What do you?
Like if I was gonna where is it at x equals 0? So my sine graph, because one of them starts at 0, 0, right? And one of them starts at 0, 1 for sine and cosine.
Oh, well, sine normally starts at 0, 0.
Normally starts at 0, 0. So
Yeah.
if I were to look at this graph, this red line here is let's just say is my x-axis. Then how much has this been shifted? If it should start at 0, 0.
And it's been shifted up
Not up. We're only
no?
looking at horizontal. We already took care of vertical. Remember, when we're inside the function, we're looking at horizontal, not vertical.
Oh, 2.
2, exactly. We shifted it to the right. Does that make sense?
Yeah, yeah. No, that makes sense. Yeah.
Okay, good. So we've shifted it to the right, which means we have to say x minus 2, don't we?
Yes.
And that's it. I've now determined the equation for this sine function. It's right up here. But in shifted form only. And then you could multiply this out if you want. I usually get questions like, can we multiply it out? Do we have to multiply it out? You can leave it like this or you can multiply it. It doesn't matter. They're the same. For Alex as well, it doesn't care.
Okay.
All good?
Yeah.
All right. So let's talk about something that looks like this. We're going to find these things. Let's just call this our horizontal shift, because I think that's a better thing that we need to worry about. And then we'll graph it. I'll show you how to graph stuff. Let me see what my last one is. Well, I only have one of those, huh? If this isn't good enough, we'll make up one. So first we want to talk about our amplitude. So what's our amplitude here?
-2.
But amplitude's always what?
Positive.
Amplitude's always positive. So our amplitude here is 2.
2.
Yes. Now, what's our period?
Is it 4?
Nope. What does 4 represent? And people listen, you're not the first one. Everyone gets these things confused. What does 4 represent?
Oh, I just found it.
I know I understand. That's our standard form. That's what we're looking at.
Yeah, isn't that? Oh, I keep
It's
thinking
B.
it's B.
Yes, everyone does this. You're not the only one. So I'm glad you're making this mistake so I can point it out. P is not equal to B. They're related, right? So
Yeah.
P is going to equal 2 pi
Over 4.
over 4, which is pi over 2. Exactly. See the difference?
Yeah.
2 pi over B. So, and that's B. So you can't get those mixed up. I know it happens all the time. Okay. And how do I find my horizontal shift?
You factor it out.
Yes. Go ahead. You're right. Say it.
So then it's factor 4 out of.
Yeah.
Is it 1/2?
No. When you factor 4 out, you divide both terms by 4. So it would be minus pi over 4. Because if you distribute, you're going to multiply them, right?
Oh, I was looking at the wrong thing. I was looking at B. Or
I
P.
gotcha, sorry. So yeah, I'm gonna factor out the 4, and now I
Okay.
can find my vertical shift, my horizontal shift. And what's my horizontal shift here?
Right, pi over 4. Like,
Exactly, pi over 4 to the right. Or in Alex, you would say positive, pi over 4. Oh, what happened? Are you still there? Oh,
yeah.
okay. But my computer just went blank. Hold on. Let me see if this helps. Okay. Okay, good. So we found our amplitude, our period, and our horizontal shift. Now what we're going to do is graph it. And here, I'm just going to do it very simply here. Let's do it very simply. Let's see if this helps. So we have our original, it is cosine. I thought I changed it. So it's cosine. So that means we're starting here and we're doing this. So this right here is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi, and so on. And then we have values in the negative direction as well. Okay. So now here what we're going to do, in my opinion, the easiest thing to do is to make a chart or a table. So here we have our original X. And I think what I'll do is I'll do all the transformations on my X value first, and then I'll do the transformations on my Y value. So I'm going to do all my horizontals first, and I'm going to do my verticals. Okay. So I start with, I have 0 pi over 2, pi, 3 pi over 2, and 2 pi. And so let's see what I need to do here. First thing I need to do is, how do I explain this? Okay, first thing I need to do is I need to do my shift. Wait, no, I'm backwards. I'm sorry. My brain is a little foggy this morning. I'm really sorry about that. It's not even this morning anymore. So first thing I need to do is I need to do my stretch compress. I need to change my period first. Okay. So what do I do? I do the same thing as I did for my period, is I have to divide each one of these by 4. So this would be X over 4. This would change the period, right?
Yeah.
And the reason I have to do each one of them, like, remember my period is 2 pi over 4 over, I'm sorry, 2 pi over 4, which is pi over 2. That's my new period. Mm-hmm. So if that's my new period, all of these values have to change, right? This will become pi over 2. So all of these values have to be divided by 4 as well. So this would be pi over 8. This would be pi over 4. And this would be 3 pi. Let's see. My computer's acting stupid. There we go. 3 pi over 8. Yeah, that's right. Okay, so I'm dividing all my values by 4 here. Does that make sense?
Yeah.
Okay. So period first, 3 pi over 8. Okay, good. And then I do my shift. Okay. So I shift this. So I take X over 4. So I take that value, and I'm going to, since I'm moving it to the right, I'm going to add pi over 4 to each one of those values. Okay, does that make sense? Mm-hmm. Okay, good. So this becomes pi over 4. This becomes pi over 8. Here, let me just do it somewhere so everybody sees. So pi over 8 plus pi over 4 is the same as 2 pi over 8. So I'm getting a common denominator. So this becomes 3 pi over 8. okay?
Mhm.
And then pi over 4 plus pi over 4 is 2 pi over 4, which is the same as pi over 2. 3 pi over 8 plus 2 pi over 8 would be 5 pi over 8. And pi over 2 plus pi over 4 would be 2 pi over 4 plus pi over 4 is 3 pi over 4.
Mhm.
Pi over 4 plus pi over 4, right? So that's all my shifted values. And since I'm done shifting, this is actually the x value that I'll use in the end. So does that make sense?
Yeah.
Is there anything about this that is confusing?
No, I think I'll just have to do the graph when I do my
I mean, this is really the best way is like once you get all your values, just put them in, and then in the end, I'll show you. So now we're going to talk about our y. So our original y that goes with our cosine when x is 0, y is 1. When x was pi over 2, y is 0. When x is pi, it's -1. 3 pi over 2, 0, 2 pi back to 1, right? That's just our normal cosine graph.
Yeah.
Right? And then let's see, what are we doing? The only thing we're doing is multiplying by -2. So this would be -2y. So this is -2, 0, +2, 0, -2. And this is my stretch or compress. If I had a shift, I would do it out here, a horizontal shift, then I would do it. A vertical shift, I would do that next, but I don't have one. So I'm pretty much done. And now all I really need to do is read the final columns. So when I want to graph it, I'm just going to graph pi over 4, comma, -2, right? I'm just reading this column and this column. So then I'll have 3 pi over 8, 0, and so on. That would be the final way to get my, I think this is I've really tried a lot of times to figure out the easiest way. I really believe this is the easiest way, is just in a table form.
Okay. Yeah, I think it's easier in table form.
Yeah, because they're, in Alex, they're going to ask you to graph the zeros. They're going to ask you to graph the maximum, the minimum. How do you find them? Well, you start with them and then you just move them. So I do believe this is the easiest way. Do you think we need to do another one? Or, I'm happy to do it if it'll help. I'm not sure. It'll just be exactly the same.
Yeah, I don't think it'll do much more. I think it's more practice.
Yeah, I think you just have to practice. And, I have office hours, and if those office hours don't work, like whatever you need to do, if you need to see me and my office hours don't work, just like shoot me an email or a text or something and let me know what works for you. And
Okay.
if I can do it, I'll just make it a separate, office hour for you. It's no problem. Okay. So the last one we're going to do, I'm not going to graph it. I just think it's not worth the time. But I want to do everything else because I think it's interesting. So I think it's a good way to just see things. So how do we find the period of this function? What do we start with? So we have to start with the period equals the new period equals the original period divided by b. That is really important.
So is it 2 pi over 5?
Yes.
Okay.
So
Okay.
this would be 2 pi. Exactly. Yeah, don't be afraid. It doesn't bite. So this is going to be 10, right?
Yeah.
That's it. We could find everything else, but I think we've done enough of that. All we have is an amplitude of 1200 and a vertical shift of 9,000.
Mhm.
Okay. So if I want to find the maximum and minimum values, I think this is really like a nice, thoughtful question. How would I do that? What do you, when you think about this, how would I find the maximum, minimum values?
Can't you use the amplitude?
That's, you can use the amplitude, absolutely. What are you going to do with the amplitude?
I don't know. I have no
Yeah, but
idea.
you're right. You will use the amplitude, but you want to think about this cosine of pi over 5t. That's the only thing that's varying here, right? That's our variable. Everything else is constants, right?
Yeah.
So, well, let's find the maximum minimum of cosine. So what's the maximum minimum of cosine?
Uh, isn't it 1 and -1?
Exactly. Make sense?
Yeah.
So if I start with those, well, that's my maximum, my minimum value of cosine. That's the only thing that changes here. So my maximum value, so P of T max, I'm going to set this cosine equal to 1, and I just add 1200 plus 9,000, which gives me 10,200, right? Because that's the maximum value cosine can be, and there's nothing else. I don't have any other options. And then P of T min is going to equal, well, the minimum cosine is -1, so that'll be minus 1200 plus 9,000. Oops, I put the wrong sign there. Which equals 7,800. So there's my max and min. I don't really have to think about the whole equation. I just have to know that since I have a cosine function, I only have a max and min of that. And so I can plug those in. And then I have an answer. Did that make sense?
Yeah.
Okay, good. And that's really the last slide I have. I'm happy to go over anything that you think I need to again. That's that's the end of what I have for you. Do you have any questions I can answer?
Well, I think I just gotta practice it.
You really do have to practice. This is really going to take practice, honestly. That's all. And while you're practicing, try to make sure you're understanding and remembering what you're doing. I think that's the thing, Alex, is you get, and I could be wrong. Like, trust me, I'm wrong a lot, but maybe what you're doing is you're trying to like do it, to get it done instead of making sure that you're retaining the information. And the trig really builds on itself. So you've got to know the basics because we're just going to keep building. You know, I know that the algebra part that we did at the beginning just went from topic to topic and nothing really got harder. It just was different. But in trigonometry, we're going to use the information that we're learning and we're just going to keep building and building on it. And it's going to get more and more difficult. You have to get this beginning information so that as we go along, it keeps making sense. Okay. That's the difference between the algebra and the trig, I think. So, and I'm not just telling you, I'm telling everybody in the class. It is really important now to start really understanding what we're doing because we'll use it again till the end of the semester. We're not going to graph a lot, but we will use the principles that we're using to answer questions. Okay. All right, let's call it a day.
Okay. Thank
Thanks
you.
a lot, Alex. Have a good one. Good luck on your, wait, hold on, let me turn off the recording.